Okay, can you hear me? Okay, I think so. So let's get started. First of all, thank you for taking the time to attend our talk. My name is Sandro Pinto. I'm Associate Research Professor at the University of Minho in Portugal. And today with me I have José, which is currently doing his PhD under my supervision. And this talk is about the future of RISC-V Heterogeneous embedded virtualization architectures. So this is the agenda for today. I will briefly discuss the first two topics, then I will hand it over to José to speak about the heterogeneous virtualization, and I will just then share some final thoughts. Well, I think you will probably hear this story 1,000 times, but there is an ongoing trend in several embedded industries to consolidate multiple subsystems into the same hardware platform. And typically these subsystems has different heterogeneous operating systems like general purpose operating systems like Linux, and also real-time operating systems like FreeRTOS. And typically the applications running atop or the workloads as different criticalities. In the context of the ISO 26262 in automotive, they are called ASIL levels, and also they typically need real-time requirements. And this is being done basically to address the so-called SWaP-C, size, weight, power, and cost, and to try to minimize these metrics. So virtualization, which is a quite well-established technology in the cloud space, start to see some applicability also in several embedded applications, because it basically provides a straightforward way for consolidation. And if you have like hardware-assisted virtualization support, you have near-native performance. And also virtualization gives you like this temporal and spatial isolation, and also the so-called freedom from interference when well implemented. Another point right now, another requirement in virtualization is the real-time guarantees. And also with this connectivity trend going on in several embedded industries, you need also security. So if you look at the hypervisor solutions, we see there is a big spectrum. On one side, we have like the traditional hypervisors available from the cloud that were somehow retrofitted for embedded applications, but because they were designed with different requirements, they have large trusting computing base, because typically they depend on privileged virtual machines such as Linux, and also they have like this penalty in terms of performance, in particular when you need to access I/O. On the other side, we have seen like the rise of several embedded hypervisors like Xvisor, and just me give you a parenthesis to know that some hypervisors are highlighted in blue because they are now supporting the RISC-V, like KVM and like Xvisor. And with these embedded hypervisors, we have this reasonable trusting computing base where you can run multiple virtual machines atop one physical CPU, but there is scaling, and they provide some sort of soft real-time guarantees. From a different perspective, you have these disruptive solutions with microkernel-based hypervisors, where there is this security by design philosophy. Some of them are firmware verified, like CL4, and you use like these capabilities, and a lot of services are moved from like the privileged level to user space. But when you need to run like a virtualization-based solution, you typically need this VMM component running at the user level. And as of today, at least for RISC-V, CL4 doesn't have this open source VMM in pretty mature state. And over the last few years, what you start to see was the rise of these static partitioning hypervisors, in particular in the automotive, in the industrial control systems, where they need like these real-time requirements. And these static partition hypervisors, where we have this open source project, our open source BAU hypervisor, you basically has typically strong real-time guarantees. But on the other side, because this is pretty static, you have typically an inefficient resource uses. So just to contextualize RISC-V, mixed criticality systems, and SoC, we are currently involved in a big project funded by the TII, where it basically aims at developing this secure RISC-V based SoC. The application is for drones, and it tries to address a scalable architecture. Small disclaimer, there are 2 talks tomorrow addressing some of these points. If you are interested, you can attend them. But in the context of this project, drones, we have this need for multiple subsystems, in particular heterogeneous operating system. That's why we are quite involved in the development of the hardware virtualization support. So, a small parenthesis to explain a little bit this RISC-V hypervisor extension that was designed for type 1 and type 2 hypervisors. It basically adds some new execution modes like the hypervisor extend supervisor and then the virtual supervisor and the virtual user. A couple of new CSR registers at the hypervisor level for hypervisor and also for guest capabilities, and also this two-stage memory management unit where you have the first stage translating guest virtual address to guest physical address, and the second stage translating guest physical address to host physical address. So, what we have done in the context of this project was basically we have implemented the hypervisor extension in the CVA6. The CVA6 is this application class core developed by the group of Luca Benini. Right now, basically it was the Ariane, now the CVA6 is under the context of the open hardware group, and I think it's Thales that is managing this core. Yesterday we had a talk from Thales discussing the support for the 32-bit because it was originally developed for 64-bit. And the extension is compliant for 0.6.1, but as I'm speaking, we are already working on the 1.0.0. And this is pretty much what we have done. We have implemented several privilege levels, the CSRs, the hypervisor instructions, all the specification. A small caveat for some CSRs are at the moment hardwired to 0 because we are expecting to implement them when we implement other specifications like the AAI, for example. And in terms of validation, as of today, what we have done, we have a custom bare metal framework for testing this edge extension or for exercising. We have functionally validated with that framework. We have also used the Xvisor white box to exercise different configuration of the page tables. And more important, we have successfully run 2 hypervisors like our BAU static partitioning hypervisor and also Xvisor and very soon KVM as well. And our colleagues from the ATH and Bologna, the groups from Luca Benini, also did a preliminary PPA analysis where they basically conclude that the introduction of the edge extension doesn't bring any impact on the timing. And in terms of area, there is an increase at around 8% in the core itself. And very good news, we are doing a first tape out coming soon in the beginning of 2022. Last but not least, we have also implemented this new extension, the Smepmp, that basically aims at providing protection for the machine mode software of accessing or executing code from least privilege modes. It basically introduced a new CSR and a few bits and a couple of other things. And our implementation is fully compliant with this 0.9.5 version of the specification. And it's very minimal. It implies very minimal change to the source code of the CVA6, and this is somehow explained with the hardware evaluation that is around 0.1% of overhead in terms of the hardware. So, small disclaimer, if you want to see the CVA6 running with the edge extension, there is a kiosk downstairs in the second floor from the TII. There is an FPGA board. If you want to know a little bit more, I think George and Rafael will be happy to give you an explanation and a tour. And we have the link down here, that is the link of GitHub where you can download, and if you have an FPGA, a Genesis tool, you can basically try by yourself. I will hand it over now to José, which is basically discussing something more innovative in our opinion about virtualization and static partition.
So yeah, so now I'm going to talk a little bit about the software work we've been doing around this project, and specifically something we are calling heterogeneous virtualization as we'll see in a few slides, is basically kind of a supervised AMP that supports multiple hypervisors. So, but first a little bit on our background. So the last couple of years we've been working on this static partitioning hypervisor called BAU. And the main goal of this kind of hypervisor is to provide, as Sandro talked about before, consolidation of multiple software stacks, multiple operating systems onto the same hardware platform, with the main requirements of achieving this real strong isolation and real-time guarantees with a real minimal TCB. So what it does basically is that initialization times, it distributes, assigns all resources to the virtual machines or partitions, and ideally it wouldn't do anything at runtime, but it needs to do some bookkeeping and like things like interrupt virtualization. So some people ask us, and you might ask yourself, why do you need virtualization to do this kind of partition, which is so simple? And the main answer, in my opinion, is that the main architecture we are coming from, which is ARM, we don't really have any standard mechanisms to achieve this partitioning without virtualization. So we're kind of forced to use this virtualization, which is not true in RISC-V. We have the PMP, as we'll see. So besides BAU, there are other hypervisors that are doing this. The main one, the most well-known, is Siemens' Jailhouse, and also the Xen project is now having a way to configure Xen in a kind of static partitioning hypervisor. So after we finished the first version of BAU, we started playing around with it, using it in some projects, and also some people started using it. And some people were coming to us asking for other features, and we ourselves saw that we needed to add some other features, and this kind of conflicted with our main requirement of having this real minimal trusted computing base, which I didn't say before. It's mainly due to certification reasons, because we really want to use this kind of hypervisors in safety critical environments. And we kind of understood that these two conflicting requirements, from one side is minimality and staticity, from the other side rich features, were kind of were conflicting one another, and we figured out that what we really need to do is decouple these two concepts, virtualization and partitioning, which we're kind of forced to use, as I said before, in the ARM architecture. So we came up with this concept of heterogeneous virtualization, which, as I said before, is nothing but supervised AMP, and we want to run multiple hypervisors on top of the same hardware platform. So we come up from, on your left side, from this architecture where we have this hypervisor like horizontally extending through all the platform, and we kind of want to move the partitioning functionality to the firmware and maybe have multiple hypervisors. So in one partition, we might have a full-blown hypervisor, a really rich hypervisor that's juggling multiple operating systems. In one of the partitions, we might have a simple hypervisor like our hypervisor that's just there to kind of give this virtual machine abstraction, or even if you have real simple software that you can port directly to this partitioning layer, you can use it right on top of the partitioning. So when we started talking about how we could implement this, we looked at OpenSBI, which is the facto firmware implementation for RISC-V, and we saw that the basic primitive that we needed to implement these partitions was already there. They're called OpenSBI Domains, and although they are not, I think the original use case for these domains was not really this use case. I think it's the main purpose is to have this kind of trust zone-like trusted execution environments. It really fitted our requirements, and you have this kind of nice device tree-based configuration, and where you can describe all the hardware resources separately for each of the partitions. But there are a few things missing so that you can realize this concept. So the first one would be to extend so the domains, of course, are separated using the PMP hardware, and we need to extend this protection to all the platform using things like the IOPMP, which is a spec that is still work in progress, but also we could use other firewall, platform level firewall technologies such as Sci-Fi Vaults Guard. The second issue is that we really need some kind of inter-partition, inter-domain communication facilities, because in this kind of systems you will have some kind of interaction between the domains, and that is not there. Thirdly, some of the main hardware controllers, like the interrupt controller or the IOMMU that would typically be under control of the single hypervisor, now we need to partition that also. So we need to add functionality for that. And finally, we'd really like to have some kind of hardened firmware, because since we are moving the critical partitioning functionality to the firmware, we really want to make sure that it's not crashing, there's no attacks on the firmware. So the first two points, I think, are already on the roadmap for the OpenSBI domain project. So I'll just say a couple words regarding the last 2 points. So first, interrupt partitioning. Here, we kind of want to have, focusing on the current interrupt controller, the PLIC, we kind of want to block access to each of the partitions to the main configuration region, where you kind of have the interrupt configuration of each interrupt interleaved with one another, and then had some kind of either trap and emulate virtualization approach so that each partition can access that zone, or even you just have some kind of SBI extension, some kind of API, so that you can access control the access to each interrupt configuration. The good news is that we can actually give direct access to the claim complete registers, which are on the interrupt critical path, let's say, which is important to minimize interrupt latency, which is an important thing on this kind of systems. So we haven't looked in depth how we do this on the new AIA specification, but we believe the approach would be similar. And just a small note is that although there is this kind of interrupt domain hierarchies in the APLIC spec, I don't think they will really fit our use case, and this is something actually pointed out in the specification, where they say that you actually have to do this kind of trap and emulate or SBI extension to provide access to the, if you want to partition this interrupt controller. So the IOMMU is also a problem. So right now there is no clear specification. There are, I think, 3 or 4 specifications around. There is no clear roadmap for what exactly the IOMMU spec is going to be. But we believe that we could follow the same approach as we should follow with the interrupt controller of either trap and emulating or having some kind of extension for the partitions to access only the parts of the IOMMU that they are allowed to. But there are another couple of things. The first is that we really need to partition also the, let's say, VMID or ACID space, because of course the TLBs in the IOMMU would be shared, and we don't have conflicting translation tables. And the last point that we were thinking about is this issue about, so if we are using an IOPMP to protect after the IOMMU, for us it was kind of obvious that the bus master ID that's used that goes through to the IOPMP is the same one that's used to go to the IMMU, but what about the access is done by the data structure page table walker interface of the IOMMU? So what privilege should the interface have? So it's not clear to us, because ideally we would want to give full control of the page tables to the partitions, and if there's no control here, we'd have also to have some kind of shadow page tables or that kind of thing. So finally, regarding the OpenSBI hardening, so coming from a really simple like threat model of, so we don't trust none of the partitions nor hypervisors, and we know that the firmware can have bugs, can be faulty. We kind of want to use the PMP and now the new version, the ePMP, to really harden it, like enforce executor right, protect per hard structures, the stack, and also maybe also protect the partitions themselves from the firmware. So now Sandro will conclude with some words.
Okay. Well, what we have done was we have discussed how RISC-V, ePMP, and virtualization extensions can be synergically leveraged to implement a flexible partitioning architecture, and basically our vision, we shared basically our vision how this can be materialized and currently aligned with the evolving specs. Just to summarize and to wrap up, basically, where are we and where are we going? In terms of the CVA6 platform, we have implemented the extension and the EPMP, but it's in our roadmap to implement or to integrate the AAI and the IOPMP and IOMMU. And then add support on OpenSBI to these components, and we already have this support for the PILIC. As we speak, we are integrating or hardening this version of the OpenSBI, and we will be happy to contribute to the OpenSBI implementation. And what we are doing with this architecture is because we really want to implement this concept of library hypervisors, where you can basically tune the hypervisor per the requirements of the virtual machine, and this is quite aligned with what you have as of today in the cloud space with the Firecracker and the RISC virtual machine market. So once again, thank you for your time, and we are now open to address all your questions.
Okay, I've got a few questions here. The CVA6 with the hypervisor extension supports a multi-core setup?
So I can take that one. So there is a multi-core version with the CVA6 that provides cache coherence. That is quite important. That is the open pit and configuration with the with the CVA6. Downstairs you don't have that version, but yesterday we have completed the integration of the multi-core version with the dual and quad core. So probably the link that I mentioned during the presentation will be updated or with that version or that support for multi-core. Yeah.
Nested virtualization seems to fulfill a similar goal to your proposed solution architecture. Can you please briefly discuss the advantages and disadvantages of your approach compared to nested virtualization?
Can you think?
Yeah, I can take it. So nested virtualization, we would think that would really go against this main idea that we want to really have a minimal layer to achieve this partitioning. So we believe that having a nested hypervisor will bring all kinds of complexity, which we don't really need. So it would be an approach, but we don't believe it's the best one.
I can complement just to say that the idea is at the moment the hypervisor is the single point of failure of your system. And if you have nested virtualization, still the lowest level of that you have in the hypervisor is still the single point of failure. What we are doing is that we are not relying on the hypervisor, and is not a single point of failure, but still a shared distributed solution, basically, something like
that. Where can I find the hardened modified version of the OpenSBI you mentioned on your talk?
I can take that one. Okay, so we have like the version is branched from one of my GitHub students. So probably we will need to understand if there is intention to upstream something, but if not, if the person wants to reach to me, I can point for the right repo. Yeah.
Does anyone have any questions?
Okay, thank you.